Let's let S be the side length of our square. Since we have the areas of these quadrilaterals in this ratio, we can express the areas of these 4 quadrilaterals as these numbers multiplied by k. So we'll sum these to find the area of the whole square. As we do this, we notice that the sum of the areas of the 2 quadrilaterals on top is the same as the areas of the 2 quadrilaterals on the bottom. This means that segment EG divides the square in half, which means that if O is the center of our square, is on segment EG. So let's redraw our square with our center O. Let's compare the ratios of the sums of the 2 other pairs of trapezoids. The area of trapezoid ABFH, it's going to be the sum of 269k and 275k, and the whole square again is 1360k. So this ratio is 2/5. So if Q is the midpoint of segment HF, then the distance from Q to side AB is 2/5 of the side length. Being in the midpoint, the distance from Q to side BC is 1/2 of the side length. That's the same distance as from O to BC, or from any of the 4 sides, because O is the center of our square. Let's take a closer look at this small triangle OPQ. We have that EG is perpendicular to HF, so we have a right angle here at P. The distance from O to Q is half of the side length, the distance from O to any of the 4 sides, minus the distance from Q to side AB. So this distance is S/10, and that's the hypotenuse of this right triangle. Let's redraw our square again. I'm going to draw this segment here. It passes through O, the center of our square, and it's parallel to HF. We'll call it H prime F prime. Because H prime F prime passes through the center of our square, it also divides our square in half. This means our 2 segments, EG and H prime F prime, divide our square into 4 quadrilaterals with equal area. Those 4 are AEO H prime, B F prime OE, CGO F prime, and D H prime OG. Each of these is 1/4 the area of ABCD. In terms of K, that's 340 times K. In the problem statement, we're given these areas. So to find the area of H prime OP, we can take 340k and subtract 269k. So up here we have 71k. We'll repeat this for the quadrilateral at the bottom. So from 340k, we subtract 275k. And down here we have 65k. Let's take a closer look at that parallelogram, H prime, F prime F. O is this midpoint, and OP is perpendicular to HF. And then we have Q over here, forming triangle OPQ. This area down here is 65k. We're going to use this parallelogram to find the area of our triangle OPQ. The area of our parallelogram, H prime, F is the sum of these 2 quadrilaterals. So we'll substitute the areas that we found above, and the area of the parallelogram is 136k. Since OQ is parallel to the sides of our square, it divides this into 2 other parallelograms of equal area. So H prime OQ is half of 136k. If this is 68k up here, we can find the area of triangle OPQ by subtracting it from 71k, and we get 3k for our triangle. We can also use the area of our parallelogram to find the distance from O to P. The area is base times height, and as our base we're using HF. We're given in the problem statement that's 34. And again, the area of the parallelogram is 136k, so we'll solve for OP. So OP is equal to 4 times k. Let's collect all the information that we have about this right triangle OPQ. The hypotenuse is S/10, OP has length 4k, and the area of the triangle is 3k. That's 1/2 base times height, so we'll solve for PQ, which is 3/2. Now we'll use the Pythagorean theorem, and we recall that S is the side length of our square, so S squared was the area. In terms of k, that was 1360 times k. So we'll make that substitution and expand everything. This is a quadratic, so we'll gather all the terms on one side and get rid of the fractions. I'm going to use the quadratic formula here, and I'll start by finding the discriminants separately. I'll replace these with their prime factorizations because I'm going to take the square root anyway. Great, we have a perfect square. So let's plug this in to our quadratic formula. It's negative b plus or minus the square root of 2 to the 14th all over 2a. We have a bunch of 2's in these prime factorizations, so let's rewrite this this in terms of powers of 2, and then we can cancel all the 2's. So we have two values for k, 5/8 and 9/40. The problem asks for the area of the square. So one possible area is 1360 times 5/8, or 850. Or for the other area, we multiply by our other value of k, 9/40, which gives us our second possible area, 360. We need to figure out which one is the true area. So let's redraw our square. If we redraw these segments, EG and HF, we can join these endpoints to create a quadrilateral with diagonals that meet at 90 degrees. Since our square is bigger than this quadrilateral, maybe by finding its area, we can figure out which of these is the true area of the square. We can do that by dividing this quadrilateral into two triangles, EHG on top and EFG underneath. They both share a base, EG, so we can factor out 1/2 and EG. HP and PF form our other segment, HF. Both of these lengths, again from the problem statement, are 34, so the area of EFGH is 578. Let's check our two areas. We notice that our second area for ABCD is smaller than the area of this quadrilateral, so that's not valid. Since 850 is greater than 578, our answer is 850. If you'd like me to solve any other contest problems, please leave them in the comments.